All right, today we're going straight under the hood of the Adaptive Harmonic Rasterization Collapse protocol, AHRC. We're going to skip the high-level theory and get right into the nuts and bolts, the step-by-step execution of how this thing actually works. So the whole thing starts with this massive question. But here's the twist. AHRC isn't trying to find some pre-existing truth out there in the wild. Nope, it's designed to build it, to mechanically force a state of provable, verifiable order into existence. And this is the core mechanism. You can really think of the protocol as a kind of truth engine. It takes in a messy, chaotic, high-entropy input, and it just mechanically crunches it down until it becomes stable and coherent. The key thing to get here is that it's not discovering order. It's actively constructing it. At its heart, this whole process is about one single transformation, taking total disorder, which the protocol gives a name, Omega, and turning it into a state of perfect, provable order, which it calls Psi Lock. This table really lays out the two sides of the coin. On one side, you've got Omega, the entropic residue. Just think of it as the noise, the errors, all the unresolved data collisions happening inside the system. And on the other side, you've got Psi, which is the goal, a state of absolute coherence where every single conflict has been perfectly resolved. Okay, but how does the system even begin to tackle all that chaos? Well, before it can start forcing order on things, it first has to understand the absolute inherent truth of each individual piece of data. It needs a pure, clean starting point before everything gets messy. And that's where the GIP comes in, the Glyph Inherent Position. Now, this isn't just a value. It's a data point's absolute, ideal coordinate in this kind of perfect, continuous space. It's the data's true identity before we try to shove it onto a grid. And this formula shows you how that truth is built. It's basically a balancing act. It takes a stable, unique identifier, the fold ID, and weighs it against its own local chaos, its entropy. And by using a universal constant like H_1, it locks that truth into a universal framework. It's pretty elegant. So here's the very first thing the protocol actually does, the zero-point query. Now that every piece of data has its GIP, the system just lines everything up in that perfect ideal order. This gives it a baseline, right? The absolute truth that the rest of the process is going to try to live up to. And now the system hits its first big wall. It's established this perfect, continuous, ideal order. But to be useful, it has to map that infinite order onto a finite, discrete grid. And, well, this is where all the problems start. This is the process called harmonic rasterization collapse. It takes that beautiful, continuous reality and forces it into a set of digital boxes or fractal addresses. But as you can imagine, when you try to fit an infinite reality into a finite number of boxes, you're going to get some conflicts. And here is exactly what that conflict looks like. Informational collisions. When the grid, the frame, is too coarse, two different truths, two completely distinct GIPs get jammed into the same box. This creates a measurable error, a quantifiable amount of noise. And that measure of error? Yep, that's Omega. But this is where the real genius of the protocol comes into play. It's not a static system, it's adaptive. It has a built-in way of detecting its own failures and, more importantly, correcting them on the fly. So now we can give Omega a formal definition. It's not some abstract idea. It's a hard number you can measure. If Omega is anything other than zero, it is concrete, empirical proof of failure. The system has failed to represent the truth, and it's violated what they call the harmonic boundary. So what does a machine do when it proves itself wrong? When it literally quantifies its own failure to represent the truth accurately? It kicks off something called the delta phase. It sees the error, it acknowledges the failure, and it immediately expands its own frame of reference. The grid size, n, doubles. It basically just zooms in, creating more resolution, more space for those clashing data points to find their own unique address. And you can see this perfectly in action right here, using this super complex Riemann zeros as a test case. At a low resolution of n equals 8, the system just fails. It reports a high Omega value, but then boom, the delta trigger fires. The frame expands to n32, it reruns the process, and just like that, the collisions are gone. Omega collapses to 0. So this self-correcting loop just keeps going, expanding, re-rasterizing, checking for errors, until every single collision is gone. And once that happens, the system enters its final stage, achieving, and crucially, certifying a state of perfect coherence.
When that adaptive loop finally successfully drives Omega all the way down to 0, the system achieves what's called Psi Lock. And this isn't an approximation. It's not a good enough state. It is a discrete, provable, and fully certifiable condition of absolute perfect order.
This whole idea completely reframes how we look at supposedly chaotic systems. I mean, think about the famous Collatz conjecture for the number 27. Through this lens, its long, unpredictable flight isn't random chaos at all. It's just the deterministic, step-by-step process of figuring out exactly how big a frame, in this case 16,384, is needed to finally resolve all its initial entropy.
And how is success finally certified? With this one single number, the global Psi score. It's calculated from the harmonic mean of the system's total coherence. A single unresolved collision anywhere in the system will crash this score. To get Psi Lock, the score has to be exactly 1. No more, no less. Perfect.
And that leaves us with a pretty profound final thought. The protocol seems to suggest that maybe unsolvable problems don't actually exist. Maybe intractability isn't a property of the problem itself, but just a limitation of our tools, of our frame. So it really makes you wonder, what else is out there, just waiting for us to build a big enough frame to see it clearly?